Welcome everybody. Thanks for coming out. Cold night. It's probably a little after 7. I don't think the presentation will take quite 2 hours like they normally do here. If I get interrupted a lot by heckling and such, it might. But let's see where it goes. So this is Introduction to Akka. That's my name. This is, again, Intro to Akka. So if you're talking about tuning and optimizing and high-performance Akka, you could always ask the Scala user group. I think there's still an Atlanta Scala user group in town, so that's where 3 guys meet once every 2 years. So, all right, so who am I? So I guess I've done a lot of stuff. I'm actually now the VP of Engineering at a predictive analytics company here in town. They're currently in Buckhead. Most of the stack is Python, so sorry. At some point, I guess, injecting Java and most likely Akka into the stack will be of importance. Up until yesterday's exit interview, I was the chief architect at AltaSource Labs. That may have been a self-given title or not, but I think, yeah. Anyway, I was an architect at AltaSource Labs. Well, okay, I'll explain SpongeBob. Usually when I go to a presentation, there's always a picture of a guy, me. But the whole point here is that you already see me here, so I never understood why during a presentation there'd be a picture of the guy talking when he's right here standing. So I figured I'd put SpongeBob on just because it's actually my favorite show on TV. So, yeah. And I'm not afraid to say that out loud. All right, the agenda was written originally before I started building the slides, so it makes no sense right now for what, yeah, sorry, for what you're about to experience. I approach these slides a little differently than I normally do when I'm talking of a specific technology. Instead of diving right into what is Akka, and here's the API, and here's how you use it, you guys can get that from the docs online, right? So what the presentation actually starts off with is the problems that Akka is trying to solve. Well, I should say there are problems, and Akka is one way to solve them. Then I will go into Akka itself, the APIs, and so on, the actor model, actor systems. There is some live code that I'll flip over to IntelliJ to show off, just because code tends to look really ugly on a slide deck. So anyway, so we'll start at the top here. I'm assuming everybody's, actually I should have backed up. Who has experience here with Akka, like actually developing with Akka? Wow, all right, 4 guys. All right, so I'll only look stupid to you 4. Just keep it quiet. So Akka is actually written in Scala, for those of you that don't know. So I'm assuming you 4 guys probably have Scala knowledge, because it's usually the Scala guys that adopted Akka first. And now it's kind of, you know, in this polyglot world we live in, it's spreading, right? Even in my Python shop. So Moore's Law, I'm assuming most of you, especially if you're an EE, are familiar with Moore's Law. It states number of transistors on a chip will double approximately every 18 months. I've heard debates whether it's 18 months or 2 years that he said, but that's the gist of it. If you take a look at this slide here, actually what's important to us, just for this conversation, green line, dark blue line. So green line is actually the Moore's Law stated, right? Number of transistors, doubling, right? So your x-axis is year by year. It's like decade by decade, actually, half decade. What happens with the dark blue line is actually remarkable, and it actually impacts where this whole presentation is going with Akka. Believe it or not, I'm starting at a very low level. What happens around the mid-2000s with chip makers is um, chips start to get really big. So this is the time of single core processors, right? So chips get really big. The actual signal had trouble reaching the whole chip in one clock cycle. You also end up with heat dissipation issues. So the way chip makers addressed this was simply to add more cores, which is how you ended up with today's, I'm sure everybody's got a laptop, or even, actually I don't know if these little things have multi-core. I'm assuming even our handhelds are multi-core. So you're living in a multi-core world, right? So multi-core processors are pretty much the norm. What that opens the door for are being able to run multiple calculations, operations in true parallel fashion, which actually Python still can't do. But but you will be able to do it with Java. So keep in mind that CPU speeds are likely not to increase anytime soon unless there's some sort of leap. So multi-core processors are here to stay. So if you're living a decade behind, the free lunch is over. The applications of today, so if you ever look at these articles that Netflix puts out or LinkedIn puts out on their wonderful architecture and their wonderful software, they actually take advantage of, they do a good job actually of taking advantage of distributed computing and the fact that you have these advances in new processors. Again, your applications could and should run in a concurrent fashion, right? This is a really bad picture that depicts not parallelism, but it's what Google came up with when I when I searched for parallelism. I got parallel parking, and I think this is like a 1980s Mercedes. So I think it's like a really old picture. But anyway, so living in a multi-core world, your applications should parallelize, and a very weak and simple definition of parallelism is when two threads are executing simultaneously. Now, enter the Java world. Everybody's familiar with Java threads, right? Mostly. If you're familiar with Java threads, you're also familiar with what a pain in the ass it is to code using the Java Thread API, and how your shared state in Java threads leads to deadlocks, live locks, thread starvation, race condition, and really ugly, nasty code that nobody knows how it works. It's always a big black box. So I actually found this on Twitter. Brian Getz wrote, he's actually became famous for writing Java concurrency in practice, and this became a very retweeted tweet by some random guy, I don't know who. 95% of synchronized code is broken, the other 5% is written by Brian Getz. I can't personally remember the last time I had to do multi-threading in Java. As a matter of fact, I think about 4 years ago, I had to build something that was multi-threaded. It was actually a big spam cannon. And instead of trying my hand at it, I was smart enough to just give it to Tom over there, and Tom built it out for us. But I still remember once that big multi-threading spam cannon came along, and actually SpringSource was a customer, and they wanted to send out an email blast, and it had to churn through 500,000 emails that had to get personalized and sent out essentially one by one. The tuning of the thread pools and all that stuff became an absolute nightmare to manage. I'm assuming most of you have had at least similar experience with Java threads. So, for those of you that don't know, Joe Armstrong invented Erlang, which is a programming language. It's a programming language that I know very little about, and all I know is the influence that it's had on Akka and the actor model in general. So out of this page, pragmatic programming, I actually picked off a few. It's actually a really long article, but I've picked off a few of the bullet points that Joe Armstrong stated really, really long ago. He compared programming languages, not Erlang, to the real world, saying things like the world is concurrent, things happen in parallel. So when I'm driving over here, I'm on 285 and there's 6 lanes of us moving all in the same direction very, very slowly. But it's all happening in parallel, right? It's not one car goes, then the other one, and then the other one, right? That's how they drive in Miami. So groups of people have no shared state. You have your thoughts, I have mine. Your state is encapsulated in you. My state's encapsulated in me. So we communicate by messages. And you'll see how Akka has actually all of these same concepts. And it communicates by messages. Now, messages in Akka can be anything. It's just an object, right? But in the real world, we use sound, light to communicate. Those messages in the real world somewhat, but in Akka definitely do affect the state of, I guess, the individual. In this case, the actor. Lastly, shit happens. So things fail, things break. And you're looking to build software that essentially takes all of these bullet points into its core architecture. And that last bullet point, the fact that your software will break, should have you thinking about building self-healing systems. Bless you. And I'm not saying in the IBM, BS marketing, self-healing machines that they put out. Akka truly is self-healing, and you'll see that in a little bit, what it offers to that respect. So there are alternatives that fit the mold of everything I've been talking about, essentially things that get around the Java thread problem. In this case, Akka adopts message passing concurrency. Again, Akka passes around messages to communicate. Using actors, if you're old like me, you will remember, nobody remembers John Lovitz? Acting, okay, all right, thank you. So it's all right. It was either that or Brad Pitt. Well, I don't know. All right, actors. So the concept of an actor is an old one. Actually, you see this a lot in technology, right? I mean, you'll see how there's towards the end of this entire slide deck, there's a whole piece on event sourcing. And event sourcing came about by Martin Fowler, which I think works at ThoughtWorks, right? The guy's like 300 years old, and he writes these papers, these blogs online, and nobody reads until 20 years later, and then they build a framework around it, right? So event sourcing kind of popped up that way. So 1973, Carl Hewitt, he actually is known for, I don't know if inventing, but his work on the actor model of concurrent computation. His actor model work actually is what inspired Erlang, Occam, and Oz. He actually has his own programming language called Scheme. Does anybody use Scheme? Yeah, one guy. All right. So anyway, he has a not very popular programming language. So actors encapsulate state and behavior. And like I said before, they implement message passing concurrency. So I'm going to get to Akka here real quick. So just giving you guys a little history. What is the actor model? So in case the actor model of concurrency. So there's certain rules you want to live by here. And you'll see how they impact your architecture and, more importantly, the scalability of your application. So actor model of concurrency, number one, share nothing. So unlike threads, where I end up with a deadlock and a live lock and all race conditions and all manner of mess, my being in an, I guess, immutable state as well, and sharing nothing means I don't have to synchronize anything, any threads, that is, right? You could think in a very simple term that Akka is providing you an abstraction to all the thread business that's going on underneath. And by providing that, you get, I guess, some utility out of it, right? So it's isolated, lightweight, event-based processes. You'll see that as those messages are passing around, they really are events that are being passed around to some degree. They're tiny. I've seen a lot of numbers on what an actor instance takes up in memory. I have no idea what that works out to. I'm an economics major, so I can't do crazy math like that. Something like 300 bytes is my guess on, I guess, the footprint of an actor instance. As you saw before, they communicate through messages. That communication is asynchronous and non-blocking, and you'll actually see some demo app and other things throughout, especially the demo app, where the entire application is actually asynchronous. So not only are the actors communicating asynchronously, but my communication with Cassandra, my communication with Elasticsearch, so my persistence layer, hybrid persistence layer, is also happening asynchronously. So asynchronous, non-blocking. Messages are immutable. Don't change me. Each actor has a mailbox. So every actor instance will have a mailbox. And that mailbox is essentially a queue that by default is FIFO ordered, right? So it's first in, first out. There are things you can do there to tune how the mailbox behaves. So you can set up priority queues. Actually, what's happening underneath here is it's actually leveraging some of the queuing libraries that are in Java under the covers. And you'll see those in a little bit. As I said earlier, shit happens. So the supervision-based failure management, all that means is that an actor has a supervisor, and if that actor were to explode for some reason, out of memory, throw an exception, whatever, the supervisor can restart, resume, or stop that specific actor. And I'll get into supervisor strategies in a little bit. That's the Akka logo. This provides no purpose at all. So since most of you are new to Akka, I don't want you guys thinking that it's just some stuff that I invented in my basement, right? It's actually used by real companies. And my former stomping grounds, Altisource, actually uses it extensively. They've actually built an entire event sourcing framework that's built on Akka. Okay, so this is the elevator pitch. Akka is a toolkit for building concurrent, distributed, fault-tolerant applications. Elevator pitch, right? So how does it do it? On the concurrency side, actors, right? So much like the threads of old, right? So a concurrent unit of processing is an actor. That's what actually buys me the concurrency. Distributed, it's actually distributed by default out of the box. I don't go into remoting too much here. One thing I do touch on is how Akka is location transparent, in the sense that when you code to an Akka actor, or when you code to the Akka actor API, where the actor actually exists, I don't care, and it should not affect my code. So it could be in a 300 node cluster, and I'm saying go create an actor, go do this, go do that, and it should work just like it's working locally on a little laptop, right? Again, the supervision side makes it fault tolerant, and I'll get into the specifics of that. Okay, so if you've ever gone to the TypeSafe website, by the way, I guess I missed this in all my little history talk. Akka is actually the ownership, I guess. I don't know. Its guiding hand is a company by the name of TypeSafe. And they also do, I think, the Play framework and maybe Spray, Scully, Spray.
Spray, Scala, Split.
Scala on Rails, whatever. So you'll see on that website a lot of marketing towards that's geared towards this building reactive applications. And the reactive applications part is essentially broken down into what the previous slide essentially had, right? So you want an application that reacts to events. It's an event-driven application. You want the thing to scale, both scale up and scale out, right? Resilient, so stuff blows up, it self-heals. Don't ask me on the last point. I don't really see how it's reactive to users because that's Bootstrap's job. Okay, so a few of my friends and I actually built a little chat application that is a heavy user of Akka. And actually, for you Spring Source Pivotal guys, the controller and service layer is actually all Spring MVC on the controller level, and actually Spring WebSockets as well, which is, I think, relatively new, the WebSockets piece. It's kind of still, what's that? Spring 4.1. 4.1, yeah, so it's relatively new, because you could tell the docs are still kind of in this state of flux. Support is in a state of flux, but SockJS, yeah. So yeah, SockJS over Stomp or whatever it is, yeah. So in this case, let's see if I could break this down. In this case, I'll actually take Gunnar here and say, Gunnar is my user one, right? And we're all sitting in a chat room, and there's, I don't know, I can't count, 40 of us. Gunnar's going to type something in the chat window and say, hello world. And that's going to hit my controllers over a WebSocket, right? So that's real time. Controller, it's going to go to a service layer. So standard architecture, no magic there, right? That service layer is going to then make an async call to my actor system. We haven't gotten into actor systems yet, and I kind of shuffled this slide around a little bit, but we'll touch it in a little bit. So I wanted to show you how everything is async here, giving me that scalability that I was talking about. So that async call to my actor system, I need my system now to do 3 plus n different things. I needed to store the message that Gunnar just sent me into Cassandra. That's an async call. I needed to store the message in some tokenized state, an Elasticsearch indexing, right? Because that's where I'm going to do my message searching. You don't want to do searching here. Things will fall over. So lastly, and probably the most intensive, if I was going to do this with threading, I need my actor system to now broadcast to each and every one of you at the same time. So there's 40 people listening on WebSockets, and they're all listening on their own WebSocket. There's no shared WebSockets here. So I'm going to spawn 40 actors and have them all shoot out over 40 WebSocket connections, basically. And all of this is happening in an async fashion. Anyway, any questions over this architecture?
Why would you choose Akka over something like JMS? Like, it sounds at a very high level they do very similar things.
I choose it because I understand it better than JMS, oddly enough. Okay. It does give me, I think, finer control over how I scale out.
It's lighter weight, isn't it? I mean, basically, it doesn't need any messaging services or any of that kind of stuff.
So I don't know, can JMS do this? Can I hit 40 WebSockets at the same time in parallel?
I'm sure you could. Yeah. You can even set up a little transaction around it.
Yeah, I don't know.
I mean,
it's not a JMS talk.
Yeah. That's fine. It's just, I see. So, well, the thing that kind of spurred all this up, is the actor system like an extra thing running, or is that
it's actually acting as a container. So
it is where your actors live. Okay. Yeah, and you can have many actor systems on the same JVM. Okay. Yeah. So, additionally, too, actually with Spring support, you could have WebSocket messages pushed out to Rabbit, because out of the box, I think it supports Rabbit queuing. Yeah. Exactly. So, I mean, that could have been another question as well, right? Why not just use Rabbit, right, to be done? So.
It's kind of the same.
Yeah, it is.
The Erlang equivalent, one of the reasons why you might choose that, the amount of scale, picking Erlang, it's not uncommon to have hundreds of thousands of processes, a process per each active thread, each active user session. So while you might choose it over JMS, is just the efficiency of it. If you need that higher throughput, you might choose over JMS.
Thanks. Actually, don't you work somewhere that invented Erlang? Yeah. So Emerson, right? Ericsson. Emerson. Right. All right, an Akka actor. So as I said before, lightweight object, 300 bytes per instance. Again, I've seen all sorts of numbers thrown around, so just call it tiny. So the actor is actually responsible for keeping its own internal state. As I mentioned before, async, non-blocking. Messages themselves are queued up in a mailbox, said before. There is a persistence mechanism that I'll discuss later on that does allow you to keep actor state. We'll get into that a little bit. Small call stack. Actors are supposedly scalable and fast. The way I've designed the actors, I guess in the last slide, they do one thing and they do it well, right? So I don't want to sit there and linger on stuff. Okay, so what happens when an actor receives a message? There's actually 4 things I think that it can do. No, actually that's right. There is supervision, but that comes later. When an actor receives a message, it can do one of these 3 things. So it either creates and spawns more actors. So consider them child actors, right? So there is a hierarchical structure here that you can build out. It can send message to other actors. The sending also includes replying, so there is that functionality in the actor framework, in the Akka framework. Designating how it should handle the next message. The Akka guys and the Akka fanboys love that because they don't shut up about it. I've never used it. It actually it allows an actor to become is the key word, and unbecome. So it essentially mutates how it would handle the next message that comes through the pipe, right? I'm sure that that has uses somewhere, but code like that, where a processing unit of work is changing on the fly, I don't like non-deterministic stuff happening. So that's just, I guess you could argue it is deterministic, but not a fan. All right, how do I scale Akka? So, like I said before, out of the box, Akka allows you to scale up and out. You want to scale up, add more cores. You want to scale out, cluster the damn thing. All right. Oh yeah, okay. So those of you that are asleep and really, really love to watch a Spring, well, not a Spring, a Maven POM file. Actually, there is some Spring coming up. So every time I see XML, I think Spring, I'm sorry. So POM XML here. So if I'm building my little chat application, in this case, what do I need included? So I have my Akka Actor framework. Persistence I'll get into in a little bit. You don't necessarily need that for the chat piece that I just showed you. Just wanted to throw it in there. And experimental really is a bad word because it actually does work. There's some history there I'll get into later. Clustering, talked about. I want to be able to log. It's always good. And then the Scala library. And that's it. I should be off to the races. I would caution you with Scala and even Akka in particular. If you're looking to upgrade your application that's already in the wild, be careful, because these guys are probably worse than Spring Source when it comes to backwards compatibility, and that's saying a lot. All right? I'm just saying that a point release will have backwards incompatible code in it. So just be careful with stuff like that. Okay, so to your question, Summer, what is an actor system? So an actor system, essentially a container that contains my actors. It is a manager for shared facilities, logging, configuration, scheduling. As I actually told Summer earlier, you can have many actor systems per JVM with different configs. We'll get into configs in a little bit. You can actually change, you can actually configure the actor systems, it seems like in 100 different ways. I'm just going to cover like 2 or 3. Millions of actors can exist simultaneously within an actor system. Yeah, so this is my Spring Source bit of code. In this case, I presumably have some class with an init method, and I'm just showing you how does my actor system boot up. Right? So I start my app up, I'm running inside Tomcat, Jetty, whatever, and I want to start my actor system. All I need to do here is actually name it, actorsystem.create, and I have my actor system. Just for gunner's amusement, we have, if I'm running a little Spring app, I'm going to define a bean and basically say, here's my init method, here's my destroy method. Spring, go ahead and start this puppy up when you boot. So that will create my actor system. Right now it's sitting empty, right? There's no actors, there's nothing in it. Destroy method. Destroy is actually, maybe one of you 4 guys can help me with my code later. Destroy is actually pretty interesting because whenever you're running it inside a Tomcat, if you don't sleep on the shutdown, Tomcat just goes crazy trying to close threads that it can't close, and then you end up with all these dangling threads. That's the reason for the thread.sleep. I don't know if they fixed that. I don't know the behavior of any recent Akka releases when it comes to Tomcat stuff, but I've always had this problem. But anyway, shutting down my actor system is as easy as actorsystem.shutdown. I will actually talk a little later on what shutdown does, because it actually has to go through and kind of kill every actor, every parent, child, and it has to slowly reap as it goes. It is asynchronous. If you do a kill on an actor, which I'll get into later, that's actually a synchronous call. That is probably why, but you would expect Tomcat to say, okay, stuff's still running, but I think Tomcat just tries to reap it and then gives up and then blows up. So anyway, that's what it is. So be mindful and go to sleep. Okay, how do I configure my actor system? So default, in your class path, what you need is application.conf, application.json, or application properties file. It's basically going to scan your class path for one of these. So in this case, application.conf is set up here, and the configuration for Akka is extremely lengthy and sometimes painful to read through. It is all documented on their website. I'll go through pieces of it where it makes sense in the presentation, but normally, I would probably never cover configuration stuff like this. Anyway, so typical configuration looks like this. I have at the top basically my logging config, log level, stuff like that. Specific actor configs are also down there. I can configure my mailboxes and how they behave. How messages are dispatched to specific actors, that's also there. On my cluster config, I'm going to go ahead and say where all of my my other nodes are. And again, some of the gurus in the room may be able to talk about the kind of the self-discovery stuff. I've always kind of, unfortunately, hard-coded the IP addresses to kind of have that automatic self-discovery, so consider it unicast. Okay, configuration again. Just as a nice to know, you don't have to use the default naming, right? Because I may want to start up different actor systems, and I want to name their configuration files differently, so I can do stuff like this on my Spring Boot, basically. Actually, I shouldn't use Spring Boot, but on my Spring init call, right? So in this case, config factory.load myconfig. It knows to look for myconfig.conf or .json or .properties file, and it's going to load that. You can also pass to the actor system a string blob, so big JSON blob that has your configuration information, but I'm not sure why you would do that, because then you have configuration stuff intermingled with your code, and that's just ugly. It'll probably get you fired. Let's see, you can also override specific values as you're loading. I don't know if you can override values at runtime, and I'm guessing you can't, because that would make things haywire. I mentioned earlier location transparency. So, little picture guide. Event comes in. I have two actor systems. They can be remote. They can be local. I don't know. They can be on the same node. They can be on different nodes. In this case, I don't care, right? Whether it's remote or local, my actors are the same, are treated the same, and like I said before, it's a unified programming model that the actor system that Akka gives me. Okay, so three main pieces that you're going to have to deal with when playing with Akka actors, and actually is the beauty of the simplicity of Akka is actually all contained in these three. That's basically it. Actor ref is a pointer, essentially. Yeah, so it is a pointer to your actor instance, delivers messages to the actor instance's mailbox. Actor ref is immutable. It has a one-to-one relationship with the actor instance. If I were to cover remoting, which I'm not, you would see how the actor ref can actually be serialized and set across the network. And I am not covering that, so don't ask. Mailbox, so message arrives in the mailbox. It's going to invoke the actor instance with that message. I'm going to cover dispatchers later on. They're actually the air traffic controller or traffic cop of of the messaging process, right? Mailboxes are slightly covered here. They can be bounded or unbounded. And again, they actually leverage the queuing mechanisms that are available in Java util concurrent package. I do actually have a sample of priority mailboxes as well. And all priority mailboxes is that I'm sending you a message, and I want you to act on this one before you act on lower priority messages, right? So I kind of break the FIFO ordering at that point. Okay, so the actor instance itself is your code. So there's your atomic unit of work. And that is the essence of the Akka actor model, those three pieces. All right, 4 actor operations. There's some API stuff here for those of you that like staring at code. All I can come up with was the 4 seasons. So, so that are the 4 horsemen. That's kind of morbid for this group. All right, so there's 4 actor operations, and there's 5 bullet points. The define is something you're doing, not the actor. So what the actors are able to do is create, send, become, and supervise. And I think I've already covered these to some degree, at least the concepts so far. So I'm going to define an actor. This is what it looks like. Public class, my actor, extends untyped actor. The onReceive is an override. That object message is the message you're passing to it. It could be anything. As long as it's an object, you could pass it in. So, and that's what's going to trigger that actor to do something, right? That's where your code goes. Okay, so there's top-level actors and there's children. In this case, we're looking at top-level actors. So right from my actor system, which you saw earlier, how I built my actor system, I'm going to take my actor system, .actor of. That props object is actually a configuration class. So having that props object, I'm passing in basically the class of my actor, which you saw in the previous slide. I'm also naming my actor, just my actor over there at the end. I've had trouble in the past when I name my actor the same thing, and you have a parent-child relationship. If every one of your children has the same actor name, you'll actually get an invalid actor name exception. So you'll see, I think, through some of this code where I actually append a name, or I append a GUID to the end of the actor name. In passing, let me see here. So defining, actually, okay. So non-default constructor, what you saw earlier was actually just the simplest actor I could create. There will come a time where you will want to pass or set actually instance variables on this actor instance. And in that case, you're going to have to alter the constructor. You can alter the constructor to have any level of, any number of arguments you want. This part doesn't change. That's still where your magic happens. You'll see the non-default constructor in action in a little bit. In this case, you know, it's back to the Gunner chat application, right? The Gunner chat application, that's what I'm going to call it. So search service is an instance variable I want to send in. You know, that's auto-wired somewhere else. So it was auto-wired by Spring externally. I'm passing that in. I don't want to do any auto-wiring here, unless I work at Altisource Labs and I want to make things really slow. That's what Scully. You can talk about that one later. The search service is being passed in, already prepped, auto-wired for me, and then presumably I'd use it here to search or to save to Elasticsearch, right? So async. All right, a create on a non-default constructor. So in this case, same thing, actor system, The only difference is I am doing props.create. Again, there's my class, and I'm passing in my auto-wired service with it. You will notice this tell, which is what I'm going to get into a few slides from now. That's actually when I start passing messages around. That's what that tell does. It probably shouldn't even be in this slide. I want you guys to wait. Pregnant anticipation. Child actors, as I said earlier, so you can have this parent-child relationship between actors, right? So in this case, my child actor, I'm calling it supervisor actor. Again, one of the things I can do with an actor is supervise the children underneath me. So my supervisor actor actually creates a child actor a little differently. It uses this get context. And that get context does a lot of things, but in this case, it actually acts as a factory for child actors. I'm naming my child actor with a GUID at the end, so I don't get stuff blowing up, right? With name clashes, basically. One thing I don't cover in this, because it probably is a little more involved topic, is how all of these actors actually sit on a path. So there is a URL, port, /user, / name of the actor, and so on. So the name is important, and it must be unique. OK, sending. 2 modes of sending. It's either fire and forget or send and receive. Fire and forget's a little deceptive, and I'll get into that a little bit. They're both async. Fire and forget, which is a tell, does not expect a reply. Now, the receiving end can still reply. It's just that it doesn't expect a reply. On an ask, we are expecting a reply, and we handle that with futures. Is everybody familiar with futures? 2 guys, 3 guys. OK, right. Fantastic. All right, so here's a tell. And my tell here is essentially one actor passing a message. Well, one actor is going to receive a message, right? This code can actually be anywhere in my code base, right? It could be from one actor. It could be in a service somewhere. So actor.tell, and it's passing a message. Again, message is just an object. I can also actor.tell message and then get self. So that's getting the actor itself and passing the reference to the, well, it's a reference from the sender of itself. On the receiving end, you can actually access the get self with get sender. And I'll show you guys that in a little bit. OK, so this is not an exercise in futures, thankfully, because they boggle my mind sometimes. So an ask looks like this. I'm going to specify the actor I want to send a message to, so actor message, and then timeout. So timeout is if I don't hear back from the actor that I'm asking within the next 5,000 milliseconds, I'm out. I don't care. Right? There are callbacks too. So there's on success, on error, on failure, I believe, and then on complete. So anyway, you could do more magic here. But remember, this is also async. Right? OK, so how does the ask work on the receiving end? In this case, this would be in some sort of on-receive method on the receiving actor. It's going to do some operation. Remember the get sender? So that's the guy that was sending me the message. I'm going to tell him the result and pass him a reference to myself. Right? I can also handle failures within my on-receive. So in this case, I'm actually telling the sender, hey, this is the exception I got. I blew up. Do something with it. And then I actually throw an exception. So it's pretty redundant code. But anyway. Become. So again, I'll cover this, but I don't know how widely it's used. So become dynamically redefines actor behavior. It's triggered by the message, so you use the message basically as a switch. Very, very simple example. Unfortunately, a very simple, incomplete example. My on-receive in this case is going to first get, let's say, a ping message. So if string matches ping, I'll print out ping. I'll increment the counter, sleep for no reason at all. Then there's getSelf.tellPong. So actors can actually do this. I can actually call myself. So in this case, getSelf.tellPong is going to pass me Pong. Now, this piece right here, this become, that's basically saying, once I've received that ping, I want you to change. And I want you to handle maybe Pongs differently, right? So presumably here I would do something different with the Pong, like I'll call myself again with a ping, and I most likely would unbecome or something here. So you could see here how the on-receive starts to mutate from one thing to another. I'm sure there are use cases for this somewhere out there in the wild that don't look like muddy code and are easy to monitor, but I can't think of any. So, all right. So supervising. This is your failover piece on Akka. So supervisors. Well, I should actually say the act of supervising is simply the ability to manage another actor's failures. Supervisors receive notifications, can react upon the failure. Supervisor strategies, by default, you have a one-for-one strategy. Define that a little bit. All-for-one strategy is also an option. Strategies can be overridden. I think you could roll your own. I wouldn't try it. So all-for-one strategy is probably the simplest to pick off. That essentially means that if one of my children fails, I can essentially shut down all of my children. A one-for-one leaves those failures more in an independent state, right, across my children. There is some sample code coming up here, but essentially my options as a supervisor is when stuff blows up, I can either resume, restart, stop, or stop my child, or stop myself, right? So a resume operation actually preserves the internal state of the child. Restart will start me from scratch, empty mailbox, right? Stop basically stops my child permanently, and I can obviously stop myself too. So those are my options.
When you restart, are the messages lost then?
On a restart,
When it empties the mailbox, is there asynchronous?
on a restart, yes, unless you are using some event sourcing persistence stuff that I'll get into later. But yeah, so yeah, state there is gone.
Quick question. On the first, it says resumes child and keep internal state. Do you mean internal state of this actor, or you mean the mailbox?
Keep internal state of the actor.
So it's not the messages in the queue you're talking about here.
It is not the messages in the queue. Correct. It is not the messages in the queue. Yeah. And there's an example. There's a really bad example coming up that I'll probably skip through, but anyway. So I'm defining a supervisor strategy here, and what I'm saying is if I see failures 10 times within 1 minute, apply something here for my child, right? So for each individual child. So depending on the failures, I can resume, restart, stop, or escalate, which were the examples, the options given earlier. I thought about going through this, but it is really, really ugly and convoluted. The idea here is that I have a supervisor service, and just high level, that supervisor service is monitoring my storage and also this counter service. If my storage fails, it should be smart enough to spawn a new storage service. But that would probably take me 15 minutes to walk through. So, supervise. So let's compare this to the Java world, right? The supervisor strategy in Akka differs in the sense that, I should say in the Java world, you get one thread to control. If that thread blows up, then it's essentially up to you to manage the failures. It's up to you to do the error handling inside of that thread, right? Which leads to your business logic commingling with your error handling code. The other issue is you don't have errors propagating between threads. So again, there's the specter of threads again. So talk a little bit about this. How do I stop my actors? So system.shutdown essentially shuts everybody, stops everybody in their tracks. Well, it's an async call. I can send a poison pill to an actor. That poison pill actually is a message, and it sits in the mailbox queue. So when the actor's done with all its other messages, that poison pill gets played, and the actor stops. As I said earlier, though, on a shutdown, and actually it would apply to any of these, parent actors wait for all their children to stop before they stop, which, again, could explain the Tomcat issue. So, ability to shut down myself, some actor. There it is again. So, child actor. There is a kill, as I said earlier, that's synchronous. All you get back is an exception thrown to your parent that you can catch, but that kills him instantly. So, stuff you've seen already, right? The untyped actor API. What's available to you? Get self is me, right? So I'm inside of an actor. This is what's available. Get self is a pointer to myself. Get sender is a pointer to person sending the message, the actor sending the message. Get context you saw when I was creating child actors. I can also get the parent and actor system information using that API call. Supervision strategy as well we saw, right? Resume, stop, fail, restart, or escalate, restart. And then the on-receive, right, which is my receiver of messages, my processor of messages. There's more stuff you can override inside of the untyped actor API. This is what a default implementation looks like. If you want anything done after the actor's been stopped, any cleanup of resources, you put it here, right? If there's any prep that has to be done before the actor starts up, you put it up there. So, life cycle, if you haven't figured it out by now, the actor of actually creates your actor instance. The resume is actually handled here, and it's different from the restart, as we said before. This actually walks you through some of the methods that I just talked about in the previous slide. The stops and the post stops and things like that are covered here on this slide. Again, it's a convoluted slide to talk through. Okay, message delivery. So 3 kinds of message delivery options that I won't say are available because you only get 2 in Akka. The first one, at most once, is cheapest, highest performance, but keep in mind that with that first one, you have no guaranteed delivery. So my message may have gotten there, may not have, And then you can get into a theoretical debate on what is guaranteed delivery. Is it the fact that I sent it? Is it the fact that the guy received it? Is it that he's done processing the message? And so on. At least once persistence is, at least once message delivery is actually made available to you using the Akka persistence experimental stuff that you saw earlier. I guess the way that it achieves that at least once is the fact that, is by way of keeping state at the sending end. When you have state at the sending end, you could end up with duplicate messages arriving on the receiving end. So you should, in this case, and again, the framework that Altisource built relies on all of this. So event sourcing relies on all this, if you're familiar with event sourcing. Martin Fowler, again. It actually relies on idempotent message processing. And that means I should get the same message 300 times and the state shouldn't change 300 times, right? Exactly once is actually the worst performance, right, when I'm sending messages. Because that means I have to keep state on the sending end. I have to keep state on the receiving end. So, I also have to filter duplicates of messages. There's an odd transition, but this is actually a complete sample of what a actor may look like, may behave like, and so on. I'm passing commands around as messages. The stuff I actually care about is actually inside those commands, but I'm using those commands to act as kind of a case and switch fashion, right? In this case, I have a user details service, again, auto-wired somewhere else. Non-default constructor. My onReceive, it's pretty simple in that when I get a process login command that's been emitted and sent to me, I am going to, from that command, get essentially an object that's within it. And all I'm going to end up doing is I want to update the login timestamp for a specific user. So presumably that command acts like an envelope, right? With all these bits inside. It's actually a crappy name because you got user login processor, but it also handles logouts. So, bad code. That's why you don't want me writing code anymore. The logging is actually handled there, just for brief purposes. That's actually going to spit out logs, spit out log lines, given the configuration you had in the application conf file. Non-default constructor, talked about. Command-based messaging as well. Here's an example of what the actual object looks like. So in my code, I have a base command, generic, and here's my process login command, right? Takes a stream event. That's actually the only property in the object. This is the calling side. So this is actually the actor creation side. Presumably somebody's logged in my Spring web app and it's fired this event, right? Process inbound event has been triggered and it's of type user login. So get my actor ref from the actor system. There's my user login processor. I'm passing that user service, right? Because we're passing that as an argument, non-default constructor. There's my GUID naming, and then this is actually going to trigger the onReceive right here, the .tel. All right, this one's for Scully, actually. Again, I could have auto-wired inside the actor, I think. There are actual hacks out there. Hacks, should I call them hacks? They're hacks. So there's miserable hacks out there in the wild that kind of provide that dependency injection, Spring framework, and Akka marriage. But most of the writing of that comes with a warning in that if you're dealing with a very high throughput system where you're spawning lots of actors, constantly creating, basically auto-wiring, those objects within an actor instance as you're spawning actor instances becomes a costly operation. So you don't want to do it in a high throughput system. And that guy's face just makes me laugh. That's just funny as hell. It's actually heard it's taken from a Japanese cartoon. So anyway. Okay. So dispatchers are what makes Akka essentially tick. They are what controls the execution of essentially messages and threads to some degree. So they are based on the Java executor framework, as I said earlier. You have two options actually when you're defining your dispatchers. So keep in mind that the executor framework is actually what provides the capability, in this case, to have asynchronous tasks, right? It's producer-consumer model. So task submission, the producer side, is decoupled from the execution, the consumer side. So that actually lets you use different threads, producer and consumer-wise. When you get into this in Akka's config, there are a lot of options for tuning. And I'm sure there's plenty of guys in the room. Actually, there's probably 4 guys in the room that will charge you $150 an hour to tune your Akka app doing this stuff. I simply just go with what's in the box in that case. So, all right. So dispatchers run their own threads. They dispatch the actors and messages from the attached mailbox. They allocate heap to the executor threads as well. So they are your traffic cop, air traffic controller, if you will. As a matter of fact, air traffic control is usually the example that's given when describing dispatchers. Dispatchers can be tuned. Looks like this. That's the executor starship. Figured a room full of geeks would know. Nobody knows. All right. Well, that's a starship called the executor. I don't know who rides around in it, but anyway. Is it the first 3 movies? Like here. It depends on what order you're watching them in, right? So, okay.
Actually, I think it appears in the 5 and 6. Only. So it's only in 2 of the 3. It's only in.
Okay.
It's actually given to him by the Emperor for successfully destroying some rebel base somewhere.
All right, so that's
Yeah.
you're gonna make me force choke you. Is that actually the ship inhabits it? Anyway, it's an aside. All right, so you have options with your dispatcher. There are 3 at least to choose from, maybe a 4th one. I think there's a 4th one that actually is used for testing. The first one, I believe, is just called dispatcher. Here we have our actors, and as you see, and you'll notice the difference with the next 2 different dispatchers. These 2 actors are actually of the same type. Those 2 are not. So in this case, this is, by the way, the default. This is how Akka runs out of the box. Every actor is backed by its own mailbox. Dispatcher can be shared with any number of actors. It can be backed by either one of the thread pools. Let's see here. In this case, out of the box, it is optimized basically for non-blocking code. The other 2, honestly, I've never used. I'll cover them anyway. So pin dispatcher, every actor is of the same type and backed by its own mailbox. However, the threads act in somewhat of a sticky fashion. So there's a dedicated thread for each actor, and that implies that the dispatcher can't be shared between actors. Now, the Akka guys say that this is actually optimized for blocking operations. So long-running I/O calls is where you would use something like this. Balancing dispatcher. There's one mailbox for all the actors. So consider it a queuing mechanism, I guess. It's an event-based dispatcher, and it redistributes work from busy actors and allocates it to idle ones. So it's an intelligent dispatcher. I mentioned earlier mailbox types. Once again, we see Java util concurrent. That's actually what allows you, that's actually what it leverages under the hood, right? For you to have all these different mailboxes. You actually see them here, right? By default, mailbox is unbounded. It's important to know that because when you have unbounded mailboxes, you could end up with out-of-memory exceptions or crazy stuff like that, right? If you let something just grow till it never ends, then that's what you get. There are articles out there that that cover how to handle situations like that, so the failure and the recovery. So when I have something unbounded, I could change it to maybe a blocking type, and assuming that, or actually a bounded type, right? Assuming my size is X, my parent can then maybe throttle down the sending of messages to mailboxes, right? So you could implement some sort of throttling to this queuing mechanism as well. So,
but if the actors can spawn more actors,
yeah,
then what's the point of that?
You'll still end up with each actor instance having an unbounded mailbox. You'll inevitably end up with the same out-of-memory exception. Even if you had one.
Even they could add infinitum, infinitely more.
Assuming one node, right? Okay. At some point, you will saturate memory, right? So the stuff I've seen online to combat out of memory, and maybe somebody's got other ideas, deals with essentially throttling of messages. I don't know. You guys seen anything?
Would that make the sending actor block then, or no?
It does. Yeah. Which you don't want to do, because in Akka you don't want to block.
But at the end of the day, you have to either drop messages or block somewhere.
Exactly.
Or run out of memory.
Or run out of memory.
So I mentioned this earlier. There are ways for you to actually roll your own mailboxes. In this case, I'm implementing a priority mailbox, and I do some sort of ordering that breaks the FIFO ordering that Akka does out of the box. So feel free to copy and paste that code and hope it works. Okay, routers. So routers are essentially what decide what actor gets what message when. Some of these names will actually look very familiar to you, right? Round robin actor. So that's going to go in a round robin fashion, delivering messages to the children, basically. Random, smallest mailbox. And then broadcast actually could have come in handy for a project I was working on. Broadcast is going to send the same message to every actor it sees. Right? That's actually handy on the chat app, right? So I want to spam out to 50 guys in the room the same message. You have 50 actors, they all get the same message. Okay, so some sample code. You can resize at runtime how a round robin router, I guess essentially how many it's round robinizing. I don't know if that's a verb. I think I just made that word up. It's okay. Okay, so futures. In this case, the top one is what not to do. Akka does give you await.result, await.ready is also an option. Here I'm doing an ask, yet I'm saying, oh, please wait for the response. I want you to wait 5 seconds. So now I'm blocking the line, right? As I mentioned before, futures have callbacks, right? So on success, on failure, on complete. Here's actually an example of a future in action. And in this case, actually, I don't know what the hell I was trying to do there. Okay, I can't even read this. That's pretty bad. Well, that's why I'm a vice president now. So, all right, persistence. You guys want to get promoted, that's what you do. You write crappy code, and they'll move you out of coding into management. So, right, so persistence. So this is actually heavily used at Altisource, and it's actually where I first became acquainted with Akka, was Altisource. It's actually an amazing place to work if you want to learn new stuff, but never actually produce anything in production. So it's a great place to learn. It's like a university, but you get paid. So experimental, as I said, so it's actually taken from a project from a gentleman that's actually now a TypeSafe employee. Was it Martin Krauser? Something like that? Yeah. He had a project called Event Sourced that got essentially merged into the Akka side. So on the persistence, the Akka persistence side, you're essentially having stateful actors, and they are able to persist their internal state. That internal state can then be recovered when the actor is restarted after like a JVM crash or something like that. As I said before, it was a brainchild of Martin Fowler. The plugins available for you at the persistence level. Actually, the guy that wrote the MongoDB plugin is sitting in the room. So you can ask him why would he do that for Mongo and not a real database? But that's up to you guys to beat him up later. So persistent actor, that is essentially your stateful actor. So that's actually an object you're going to be using. The journal is actually where the states are held. So these databases are your journals. You could think of them that way. Again, at least once delivery. So I actually have some guaranteed delivery, but I also have to code once again in a fashion, in a way that protects me from state changes by the same message, right? So I have to be able to identify dupes and so on. I can also take snapshots as I'm processing, but I'll get into that a little bit.
So you persisted the messages or just the state of
the internal state of the actor?
What about the messages?
The durable mailboxes are gone.
Yeah, they were really replaced by actors.
Yeah. So.
Yeah, the event sourcing stuff, I think that was at Altisource. The events that were coming in would be turned into messages, I believe, but those were serialized and persisted as well. And because I think they were idempotent, right? Idempotent. You can replay all those events all over again and not expect dramatic changes, I guess, to the system, right?
Right, yeah, so the journal stores the sequence of events, and each one of those events indicates the state. So when you replay the events in the journal, you get to that.
So what happens to the messages if, for example, the message, some object that needs to be persisted and server died? Where does the message go? assume that's where you might want to use JMS. So your state might be persistent because your message lives if the system goes away.
So, as the messages are received by the persistent actor, they get converted to events. Events get persisted into the journal. That ends up being a persistent story.
I see. So okay.
So you're storing essentially the small changes that you define instead of the message.
Okay, here's my attempt at doing some cartooning here, so just bear with me. So I guess to better explain the whole persistence side, try doing this. So with no persistence, I'm essentially looking at this. Here's my message. There's my actor, and its state is 0. My message arrives. I increment the counter. Counts 1, right? Oops, I crashed. Okay, so far not a very funny cartoon. So no persistence again. I'm going to go ahead and restart. So clean restart of my actor. I'm going to send it another message. And this is post restart. I've sent it another message, and actor says count 1. Well, that's wrong because that actor instance actually should have spit out 2, right? So with persistence, again, the journal DBs, Mongo, Cassandra, HBase, LevelDB. I don't know what else is supported, but that runs the gamut. In this case, my journal actually has 2 messages in it, right, sitting in my database. And post restart, I should get my count to 2. All right, so it's not the most clever of cartoons, but you get the idea. It's basically what Scully said. I didn't want to go into the event sourcing stuff, and oddly enough, I keep covering it. I covered it at the Elasticsearch stuff too, Elasticsearch presentation I gave. There's a lot going on here in the sense that there's event sourcing. There's also the concept of CQRS, right? So I have a different, assuming I had some crazy storage backing here, there is the concept of my write side and my read side, right? So there's a division of responsibility. This is actually a lot like the stuff that the real servicing team at Altisource is building. They've actually built this framework, and the applications will actually be over here digesting the events that are being emitted. And as Brian said, you should be able to replay those events and not cause catastrophes from happening on that side. So, all right, event bus. So this is actually quite helpful, and I have some code as well. So the event bus is known as the event stream, I think, internally. It's actually messed up. So internally to Akka, it actually knows the event stream. The concept of an event bus is used internally, and it handles dead letters, logging, etc. I did not cover dead letters. That may have actually helped answer your question a little better. Dead letters are essentially messages that have nowhere to go. So under your example, right? And those dead letters are then broadcast out on the event stream. Presumably, you could listen in the event stream for those dead letters and do something with them. Right? Issue with the event bus is that you are broadcasting out. You don't have any access to the sender, the emitter, essentially, right, of that event. Okay. There are 3 pieces to keep in mind. There's the event. So you're going to see there's a class type that you're essentially listening for. The subscriber is a subscriber that's allowed to register on the event bus. The classifier in this case, to be used in selecting subscribers for dispatching. And I'll, let me cut to the code, I think, here. Real quick. By the way, these examples are actually available on my GitHub. They are Akka examples in Java. All right, this is going to be a little kludgy. Here, that's clearly Gavin King was smarter than I when wrestling with his projector. That's saying a lot. All right. Okay. So in our case here, here's my main method. Creating my actor system, I'm actually creating an emitter and a handler. So the emitter is going to place an event on the event bus. The handler is simply going to be sitting there listening for an event of that type on the event bus. So very simple system here in that I've created my emitter and my handler, and I'm saying, handler, listen to events of that type. And my emitter, actually in this case, the emitter is getting called, right, with a command 10 times. 10 times. And I am going to publish on the event bus a new event of type event. Probably could have been better with my naming, but a new event of type event with some data in it. So I'm not technically sending actor-to-actor messages at this point, right? I'm actually publishing to an event bus, and this guy is simply going to process the event that it hears and has subscribed to on the event bus, right? Because it's subscribed to events of that type, of that class. Right? You can't. The on-receive is object. It's an override, and that's, yeah. All right. Okay, so.
So with that example, when does it make sense to spawn off kids? Would you supervise an event bus type application?
In the previous example, well, so the example I gave initially, which Summers wanted to shove JMS in there, that actually makes sense to spawn off children, right? And that I have one actor that's responsible for creating a Cassandra insert, an Elasticsearch insert, and maybe he doesn't create, so those are two children, right? So I have Cassandra, Elasticsearch, the two children get asynced. And then maybe I use the concept of an event bus. I'm going to publish this chat message on the event bus, and I have a set of actors that now take that message and socket it out, right, using WebSockets.
Would those be separate actors, or would that be an actor that has kids that it's spawned off?
Depends how you design it, but they would probably be, actually the way it was originally designed, it would be one actor that collects who should be getting these messages, right? Who's logged in and who's listening on a WebSocket, right? So you'd have some sort of clustered session information that you're polling, right? You're going to pull from. So that actor would be the parent, and he would spawn actor per, I don't know.
So he would spawn the kids and say, go listen to the bus, or go?
Or go socket out. You could have, yeah, I'm not sure where you're going with this. I mean, you could have a parent that that oversees handlers, right? So oversees subscribers. I guess that's where you're going.
Well,
you know, in my mind, upsell, it's, you got a bunch of subscribers going and grabbing information off the queue essentially a bunch, right? So if I've got one actor that's supervising and spawning off multiple kids, well, the kids smart enough to know and go look at the plus, or is
The kids,
Yeah, the kids can be subscribers as well. Yeah. The kids are actually no different from the parent by capability or by type. Yeah. I actually didn't cover more than this. There's a lot to Akka. I didn't cover testing. Typed actors, just because I've never used them, didn't feel like learning it. Application monitoring, I think TypeSafe actually offers a commercial monitoring solution. I don't know if there's a free one. There is a free one?
couple.
Common one is Paymon.
Paymon.
Hot type.
What?
Hot type. That's HAWTI.
Never heard of it. Okay. And that's free?
That's free.
Okay.
Like I said before, I didn't cover remoting. You could probably do a presentation just on remoting. And the configuration options, there's the link. It's about 10 pages of scrolling on all the different levers and pulleys you can do. So, all right, so my stuff that have the Java examples is up there. So you'll find a lot of Akka Scala examples on the web. And actually the Akka documentation is in two flavors. That's Java doc, not Java doc, by the way. And point here is that the Akka website provides the documentation in two flavors. So it's the same exact documentation, except that all the examples are either in Java or they're in Scala. It's actually really, really helpful.
How much adaptation do you have to do to move from the Scala actor model to the Java actor model?
I would assume your architecture stays the same, but your language has completely changed, right? Yeah. You'll have an easier time hiring people. That helps. I mean, there's maybe, well, that I know of, there's a handful of Scala shops in town. And finding seasoned Scala guys is difficult in this town. As a matter of fact, I think half of the guys that we're talking about are sitting in this room, oddly enough.
If you do a search if you ask GitHub for all the primary Scala developers in Atlanta on GitHub, there are about 30.
Wow. So
maybe a good thing to learn, right? I mean, if it's could demand a higher price, I guess. But yeah, I don't know, and it's a mixed bag, right? So Altisource uses Scala, and then you have a startup using Scala. There's a TST is the well-known one, right? If everybody knows John Steelman, right? He runs that thing over there. So they're a pure Scala shop. Yeah, I don't know if they use Akka though, but definitely Scala. So 30 guys, a huge city. So any questions? I think I finished right on time. I thought it was only going to be an hour. But yeah.
Is it one thread per actor? Is that a configuration thing? Is it bound?
It's a configuration thing. And it goes into how you set up and tune your dispatchers. That's what's going to determine, is it thread per actor or thread per many actor?
And if it's thread per actor, I mean, is there a bound?
that's also configurable. Yeah. So.
Are the actors reused, or are they garbage collected when they're done processing their message?
That's actually a good question. In my experience, they seem to stay around. Now, I don't know if it's my configuration, but it seems like I can scale out to meet demand massively, but then again, it's 300 something bytes each, right, that are sitting there doing nothing, right? But they never scale back. I don't know how you guys handle it. I mean, is there a reaper that goes through and kills child actors that are idle?
Just do poison them. You're done with them, kill them.
So, in other words, it has to be verbose, Lance?
We have this thing where we're using full passivation. Basically, after the timeout happens, we cause the actor to save its state, using persistence, and then shut it down.
Yeah, you can set up a receive timeout so if it doesn't say this. So if it doesn't receive a message in a certain amount of time, then
So Mission Impossible is itself.
How does normal Akka and then it looks like the new kid on the block is like Akka Streams, right? The whole reactive programming model, whatever. How do you go from that? I guess it's the next step, kind of the framework on top of Akka. How does
I know nothing about Akka Streams. Okay. I don't know. Maybe the Scala guys can tell you. No, and
it's really new, so I don't have anything.
Too new. That's your next presentation.
Does anybody work with Akka and Camel together?
So there are actual, there is pluggability with Akka and Camel, Akka 0MQ, other stuff. I've never worked with it.
yeah, it's actually, it does integrate fairly well with that specific module for the handle.
Maybe something else I should have covered, or put on my stuff I didn't cover slide.
Are there any performance benchmarks that you know, or?
There are. I refuse to add them to my slide deck. I worked at JBoss for a lot of years, and benchmarks are bullshit, right? We would put out a benchmark, then BEA would put out a benchmark, and then, right, IBM, and it's like how these guys tuning stuff, and what are they doing? It's like sorting operations or doing this. It's like the benchmarks don't mean anything really. There are benchmarks online that you could find not only on Akka Actor Processing footprint, but also there's a lot of information on the two type of thread pool executors. So thread pool executor and then fork join executor. And they'll graph out, but again, what are you doing, right, where one is better than the other, right? So yeah, I didn't want to do that because I know it would, a lot of times benchmarks will cause an explosion, right? It's like, where do you get those numbers? Who's coding that? So.
Where do you see the primary use for this? Processing large data where it's not interacting with a consumer, or does it play well with e-commerce site or something like that?
That's funny. So one of the interview questions that I've gotten in the habit of asking people, even junior engineers, actually Ben went through it back there, was here's a whiteboard marker. I want you to get up there and design all of Amazon.com, right? Would you use Akka for Amazon.com? On the front end, is what you're asking basically, on the user side, right?
Yeah, I can certainly see delivering, sending out payments or passing messages to all the delivery suites, but interact with the browser.
So so interact with the browser, I guess the metric I would use, if I need a synchronous operation or immediate feedback, immediate consistency, I probably would think twice. If eventual consistency is okay, which most of the systems that I've built and worked on, eventual consistency was okay. As a matter of fact, the fact that they were not async caused more problems scale-wise, right? So if you just take the Amazon side, so e-commerce, when somebody's adding stuff to their shopping cart, would you use Akka? Maybe, right? When somebody's doing a search, probably not. right?
Yeah, so certainly, definitely, the microservice components of your overall web app.
And well, I guess part of your question also had large blocks of data. I believe Akka actually sits inside of Spark with a lot of Python code, I think, too. No? Is there not Python? Just threw that out there. But Akka actually is the engine that fuels Spark, if you're familiar with Spark. Okay, that's my next presentation.
I have a couple of questions, I guess. One of the things kind of early in the talk, you talked about Akka as a whole being non-block.
Right.
I think that was one of the things, right? Is it literally lock-free, or is it? I mean, are all the data structures lock-free?
Yes.
No. Okay.
Yes. Again, but you saw examples where you
Except
could make it.
Stuff.
Yeah, you could make it block.
Yeah.
But out of the box, unless you're going out of your way, there's not going to be locks. There's not going to be blocking. It is an async framework.
The key to that is the immutability, right?
That's exactly the case. The not sharing of state. Yes.
Right.
The encapsulation, right? The actor encapsulates its behavior and its state.
And obviously the queues have to be block-free as well, because that's where everything's.
Queues as well, yeah.
That's the handoff.
And that's where you saw the Java util concurrent leverage and stuff like that.
Is there any attempt to run actors as the dispatchers kind of run the show, scheduling things? Is there any affinity between actors and processors, so that the data that the state that an actor actually controls, because an actor has mutable state, right?
Yep.
So that it's constantly run on the same processor as opposed to moving around.
So you want to determine where the actor is at a given time?
No, I just want there to be good cache behavior. So I'm wondering if there's some smarts in that dispatching piece that kind of takes all that stuff into account to try to.
The dispatcher to me is engineering term. It's FM, right? It's bucket magic. It's actually an engineering term.
So it technically, that thing could be as smart as possible.
Yes.
Get the best performance out of the system.
Yeah, I'm going to take the Akka guys at their word when it comes to dispatch. Now,
in general, in Java, it's hard to get core affinity down. So, unless they're doing J and I magic, then it's probably not happening.
The dispatcher configuration as well can be tuned to an nth degree. I didn't cover that at all. Yeah. More questions? 9 o'clock on the dot. Everybody gets home and snuggles by the fire.